It's funny. We never really think about the invisible engineering that keeps our cities running, that keeps us healthy. Well, today, we're going to pull back the curtain on one of the most vital systems out there. We are diving deep to decode the actual blueprint for clean water. It really all boils down to one simple question, one we almost never ask. What actually happens after you flush? It's something we do every day without a second thought. But the answer, well, that's where things get fascinating. Because the answer isn't magic, it's some seriously meticulous engineering. And we've actually gotten our hands on the design document for a real wastewater treatment plant. I know it looks like a wall of text and numbers, but you should think of it as the secret recipe that engineers use to turn waste into clean water. So, you ready? Let's start decoding. All right, so the journey for this water kicks off at the very entrance to the plant, in a section they call the headworks. The first job is pretty physical. You got to get rid of all the big stuff. And this isn't just about cleaning up a bit. It's about protecting the incredibly delicate system that comes next. So before they can filter anything, engineers have to know exactly what's coming their way. And that means precision starts right here with the very first calculation on the blueprint, the flow rate. Literally, every other part of the plant's design depends on this one number. How much water is showing up, and just as important, how fast is it moving? And the sheer scale here, it's just mind-blowing. This plant is designed to handle a peak flow of 2,778 gallons, not per day, not per hour, per minute. To put that in perspective, that's like almost 50 bathtubs full of water rushing into the plant every single minute. But it's not just about how much water, it's about speed. The velocity is everything. See, if the water moves too slowly, all the heavy stuff like sand and grit just settles in the pipes and clogs everything up. But if it moves too fast, it'll slam all that debris into the filtering screens and break them. It's this incredible balancing act, right from the get-go. Okay, so the big stuff is gone. Now the water moves to the real heart of the plant. We're heading into the biological powerhouse, where a literal army of tiny, microscopic workers is about to take over. And the heroes of this whole operation? They're called activated sludge. Yeah, I know, the name doesn't sound too heroic, does it? But this is a carefully grown, living city of billions of microorganisms, and their one job in life is to eat all the dissolved organic pollutants in the water. They are the ultimate all-natural cleanup crew. But to get their job done, this huge workforce needs a place to live, and a really, really big one at that. Which brings us to this next part of the blueprint, designing what's called the aeration reactor. This entire page of math is all about building the perfect home, this massive tank where these microbes will live and work. So just how big are we talking? Well, the calculation here calls for a volume of over 1.8 million gallons. It's hard to even picture that, right? That's a tank big enough to hold almost 3 Olympic-sized swimming pools, all just to create the perfect home for bacteria to clean our water. So how do the engineers know how much work these little microbes even have to do? They use a metric called biochemical oxygen demand, or BOD. Now that's a fancy term for a really simple idea. It just measures how much food, aka pollution, is in the water. The higher the BOD, the dirtier the water, and that tells the engineers their little microbes are going to need a lot more oxygen to get the job done. Which brings us to this beast of a calculation. I know, right? This is the formula for what's called the standard oxygen transfer rate. It looks super intimidating, but its purpose is actually pretty straightforward. It's all about figuring out the exact amount of oxygen they need to pump into those giant tanks to keep that microbial city breathing and working perfectly. Let's break it down. Really, this formula is just a 4-step process. First, it figures out the basic amount of oxygen the microbes need for all the food that's in the water. Then, and this is the clever part, it corrects that number for real-world conditions, things like the water temperature and even the local atmospheric pressure, because both of those things change how oxygen dissolves in water. What you're left with is the final, super precise amount of air to pump in. Okay, so our microscopic workforce has eaten its fill. The water is way cleaner, but now it's mixed with all this heavy, well-fed sludge. The next mission-critical stage is separating the clean water from the solids. This all happens in these huge tanks called secondary clarifiers. The idea here is actually really simple. It's like letting a glass of muddy water sit still. All these calculations you see here, they're just for designing these tanks so the water slows way, way down, which lets all that heavy sludge gently settle to the bottom, leaving perfectly clear water at the top. And once again, it is all a balancing act. The blueprint shows that the water has to sit in the tank for over 7.5 hours. That's the patience part, to give the solids plenty of time to settle. But at the same time, the plant has to be efficient, so it's skimming that clean water off the top at a rate of over 600 gallons for every square foot every single day. That's the speed. Patience and speed perfectly engineered to work together. All right, we are in the home stretch now, the final step inside the plant. The water looks crystal clear, but it's not quite ready to go back to the river. It needs one last, absolutely crucial polish to make sure it's completely safe. This is it, disinfection, the final line of defense for public health and for the environment. Because even though the water looks clean, there could still be invisible, harmful pathogens in there. You could argue that these final calculations are the most critical of all, making sure the perfect dose of chemicals is added to take care of anything dangerous that's left. And I mean, just look at the precision here. The recipe calls for adding chlorine at a rate of just 3 to 10 parts per million. Then, to make sure the aquatic life in the river is safe, another chemical, sulfur dioxide, is added to completely neutralize that chlorine before the water is released. It is the final, careful touch that protects absolutely everyone downstream. But wait, what about all that sludge we worked so hard to settle out? It doesn't just disappear. This one plant produces over 2,300 pounds of solid waste every single day. That material gets sent to these huge drying beds, which need about 21,000 square feet, roughly half a football field, where it's dewatered and prepped for its final disposal. So when you step back and look at the whole thing, it's really something, isn't it? On one hand, you have pages jam-packed with dense, complex calculations. And on the other hand, what's the result of all that? A simple, clear set of parameters that guarantees the water leaving the plant is safe for all of us. In the end, every single number, every variable, every formula in this entire blueprint, it's not just abstract math on a page. It's the direct line to the concrete reality of protecting our health and our environment every single day. It's just this incredible, invisible system humming along 24/7, all born from a document just like this. It really makes you think, what other amazing, complex systems that we rely on every day are out there, hiding in plain sight?